Hello, everybody. So, we are still talking about the mechanical energy devices, and in this video, we're going to discuss the energy devices in more details. So, we already know the difference between a turbine and the pump, and that the two are used to convert either mechanical energy into electric energy or work, or the other way around. But I want to go back to the definition that we discussed before about the mechanical energy devices and um, the mechanical work or the mechanical work or mechanical energy. I'm sorry. When we said that the mechanical energy is the form of energy that can be converted into mechanical work completely and directly, and we already discussed this by an ideal mechanical device. And we now know what we mean by mechanical device, but here is this word, um, the word ideal. This is what I want to be discussing in details today. So, to understand what we mean by this word ideal, let's first discuss the components of a pump or a turbine. So we all know now that the mechanical work that or the energy that is provided to the fluid comes I would say in 99.99% of the cases from electricity. This is the source of energy that is used to generate mechanical work or mechanical energy. So the pump, this is a pump. The turbine is very similar, but I'm going to be discussing the pump because this is the photo that we have. So it consists of two main components. The first is uh, the motor. This motor is just a device that consumes electric energy to produce mechanical energy. Okay, this mechanical energy is in the form of rotation. It's a shaft that rotates. This motor is very common. It's you must have seen many of these motors. If you have played with little car that works with batteries. What rotates the wheels of the car is this motor. It's like a thick thing that has a little metal bar coming out of it. So this is the same concept. It's just bigger, but it's the same thing. So it converts. So the motor is just something that converts the electric energy into mechanical energy in form of shaft work. This thing coming out here is called the shaft. So this is the metal bar that rotates as a result of the electric energy that is provided to the motor. And there is something here that's called metal coupling. So this coupling is just something that is connected to the shaft that can connect to another shaft to transfer the rotation from one or from the motor to whatever thing that you want to use, whether it's a car wheel or any other thing, or in our case the impeller. So the shaft work comes from here, rotates. This shaft rotates, and this coupling transfers this rotation into this other part, which is an impeller. So the impeller is like a fan. It's encased in this casing, this metal, the blue metal casing, and it rotates very quickly. So there is like a fan that rotates very quickly, and this rotation is what provides the energy to the fluid. So the fluid comes from here. The fan or the impeller rotates very quickly, and as it rotates, it increases the kinetic energy and the pressure of the fluid. So the fluid coming out here is has more or much higher energy than the fluid going in from here. Okay, so this is the impeller. So these are the components of the. It's mainly the motor and the impeller and the shaft work being transferred from here to there. So the this is the pump. The motor is I mean the the generator is, I mean, the turbine is the same, but the energy flows in the other direction, meaning that the mechanical energy flow comes from here and exits from here. It comes out very, I mean, it rotates the impeller very quickly. Then the impeller rotates the shaft. This shaft transfers the rotation to this component, which is now called a generator. It's not a motor, it's the opposite, it's a generator. So this generator converts this rotation or the shaft work into electric energy. So it's the same setup, but the direction of the energy is the opposite. Now, based on what we said, these are the components of the pump. So I will discuss here the direction of energy or the component or the energy transferring from one unit to the other. So we start here with electric energy in. This is in because it's going into the pump or into the motor, and this comes out as shaft work out. It's shaft work out of the motor. Okay, so the input to the motor is the electric energy, and the output is shaft work. On the other hand, for the impeller, we have shaft work going in and mechanical work going out, or what we call delta E mechanical, which is the difference of energy between the output and the input. So we call it delta E mechanical. Both are the same. And so for the impeller, the shaft work is converted into mechanical energy. The input is shaft work. The output is the mechanical energy. And as we said before, the turbine is the opposite. So in case of turbine, the energy goes this direction, and this direction. So it's all the arrows are flipped. And of course, this is going to be mechanical work in. This is going to be shaft work in because it's going into the generator, and then electric work out. Okay. So, anyways, this is the flow of energy. Now let's go to the point that we are going to discuss here, which is about the ideal pump. What we mean by an ideal pump or an ideal turbine. And the reason we went through the discussion on the components of the pump is the definition of ideal pump, or understanding what we mean by ideal pump depends on what we covered here. So to understand what we mean by ideal pump, let's consider a case. This is the same thing as here. Okay, this is the same setup. It's a motor, a coupling, and an impeller. It's the same thing. So let's say we have electric work going in, and this electric work should be converted into shaft work by the motor. So we have 100 watts going in. Ideally, this is what we say, this is the ideal case, that all the 100 watts are going to be converted into shaft work. And this shaft work that's going into the impeller, that all the shaft work will be converted into mechanical work. So we have 100 watts going here, coming out here as 100. This is going into the impeller, coming out as 100 watts. So we consider in the theoretical pump that all the electric energy will eventually convert into mechanical work. Okay. But this is right if it's an ideal pump, meaning that this is the theoretical case. But in reality, this doesn't happen. In reality, what happens if we have 100 watts? Of course, these numbers are for demonstration only. That the shaft work would be 90. Not all the 100 are converted into shaft work, and this 90 watts of shaft work are not totally converted into mechanical work. So we will end up with 75 watts of mechanical energy or mechanical workout. And the reason is very, very simple. If you've ever seen a pump or a turbine that's working, you would notice that there is heat coming out of the pump, there is noise, there is vibrations, or there are vibrations, there are a lot of energy losses that happen. So these losses are what cause the decrease in the energy from electric to shaft, and from shaft to mechanical work. Okay, so this is why we don't have any pump ever that we can consider an ideal pump. It will always have some losses which will make it non-ideal or real pump. And of course, for the turbine, the flow is the opposite. So if we have 100 watts going in here, we will end up with electric energy of 70, 75 watts for instance. And so it's going to be less. Okay, so based on this deviation from the ideal case, we have a term that we are going to use, which is called the efficiency of the pump. So the efficiency of the pump is a term that we calculate to tell how far the or how close or far the pump performance is to the ideal performance. This is just to know, is it performing well or not performing well. And the efficiency is giving this symbol, which is called eta. So this eta is considered the universal term that is very, very commonly used to express the efficiency. So it's a term that you will see a lot later. Yeah. So this is the symbol that we have, and it's calculated as the ratio of the actual performance to the theoretical performance, meaning that what happened relative to what should happen. Or the other definition, which I personally prefer here, is that it's the ratio of the output to the input. It's the ratio of the output to the input. So we can apply this concept on each component. So for the motor, efficiency, if you want to calculate the efficiency of the motor, the output is the shaft work, the input is the electric work. So the efficiency of the motor is the ratio of the shaft work out to the electric work in, which is 90 over 100, which is 90%. For the impeller, we have the input is shaft work out, the output is mechanical work out. So it's going to be the mechanical work out over the input, which is the shaft work out. And as we said, mechanical work can be considered as delta E, which is the energy difference between the fluid in and out, over the shaft work out, which is 75 over 90, which is 83.3. Of course, these numbers are for demonstration only. This is just to give you an idea how the efficiencies are calculated. So this is how we can calculate the efficiency of the motor and the efficiency of the impeller. Now the other case, if it's a turbine, the energy direction is the opposite. So we can still calculate the generator efficiency, which is the output over the input, which is the electric work over the shaft work in, which is 65 over 88, so it's around 74%. And for the impeller, it is the out over the in, which is shaft work out over the mechanical work in, so it's 88%. So this is the efficiencies that we can calculate. Now, it seems nice and simple and very easy to deal with, but there is one thing here that will make the use of these terms not very, or the efficiencies not very practical. This is or depends on our ability to measure the different terms in these efficiencies. So we know how to measure the mechanical work. We can measure the energy in and energy out of the fluid. We can measure the pressure, the flow rate. We can know, the velocity. We know how to measure the height. So we can tell if there is a difference or the value of the difference between the two, the energies of the two fluid streams in and out of the pump or the turbine. So this is a measurable term. We have devices that measure the electric power consumption. So there is, it's like what we have at home. We can know how much electric energy we're consuming. So we know how to measure this term and this term, but there is no way we can measure this term. It's part inside a device, and it's a moving part. So it's not a practically measurable term, which is the shaft work. So dealing with the efficiencies that contain the shaft work is not a practical thing, which makes the two efficiencies that we have here for a pump not practical efficiencies for practical use. So in order to make the efficiency a more practical term, we need to get rid of this shaft work. And to get rid of it, it's very simple. By looking at these two terms, if you multiply them together, you can end up with the mechanical work to the electric work in. So it's the ratio of the mechanical work out to the electric work in. And now we don't have any shaft work in this term. If you look here, you would see that this term relates the output of the whole device over the input of the whole device. So this is considered, it's an efficiency, but it's not efficiency of a single part of it. It's the efficiency of the whole device, of the whole pump. So this relates the final output to the initial input without dealing with what is in between. And that's why we call it an overall efficiency, because it's the motor efficiency multiplied by the impeller efficiency. Okay, and this is what's really practical, and this what really matters with us. I don't care how much energy is lost in the motor and how much is lost in the impeller. Of course this might be useful if I want to improve the performance of the pump, but for the practical use, I don't care. What I care about is the final mechanical work out and the initial work, electric work in. And this is what really matters, because if I'm using I do, and this is what we will do later. If I'm doing calculations on a pump and I want to know how much energy, electric energy I need, then I have to know how much mechanical work I need to provide to the fluid, and from the efficiency I can find the electric energy. Okay, so this is how it works. The same for the turbine. So the turbine efficiency, if you recall the generator efficiency and the impeller efficiency, will have the same issue that the shaft work is in there. We cannot use the shaft work, so we can multiply the two terms together to get the overall efficiency of the turbine, which is the electric work out over the mechanical work in, which is the ratio between the final output and the initial input. And this way we can get the overall efficiency of the generator. So this is what we want to discuss regarding the um, uh, efficiencies of pump and turbine. The efficiency is a very, very important term, because this is what makes our calculations real. We do our calculations on theoretical pumps, but then we can, or turbines, but then we can use the efficiency term to make the numbers more practical. So starting next time, we will start with the conservation of energy equation. We already covered what we need to cover before going into the details of the conservation of energy equation. So we will do this next time, and I'll see you then, inshallah. Goodbye.